Hey, put that away. I'm not taking it. It was 20 minutes ago. So what we're looking at today is we're going back to the exponent rules. And towards the middle half end of first semester, we talked a lot about stuff like this, where it's x cubed times x squared, and what did we do? Yeah, x to the fifth. Good. So what we're looking at is going to be the same style stuff, but we're going to talk about it in terms of rational exponents. Now, what that means is that we're going to be looking at that. Exactly. The properties will not change. You just have to worry about the x. We're just using the same exponent rules, but now we're just going to do it in terms of the rational exponents. So if we have 1/3 plus 1/2, what would you have to be able to add them together? You'd have to have a common denominator. So this would be, what would that be? 2/6 and x to the 3/6, which gives you x to the 5/6. This is what we're talking about today. Okay? We're going to talk about this. We're going to look at how we work with numerical stuff. We're not going to get too far into simplifying radicals and exponent rules with variables probably today, because there's a lot of other rules that we're going to look at. We're going to talk also about, remember when we did this, you've been doing this for a long time, if it was 2 divided by the square root of 3, was it proper to keep the radical in the denominator? No. What did you multiply top and bottom by? By the square root of 3. Because what, in fact, is the square root of 3 divided by the square root of 3? 1. You're always multiplying by some factor of 1 to be able to, what we call rationalizing the denominator. So in this case would give you 2 root 3 over 3. Well, here's what you're actually doing. What's a square root in terms of an exponent? It's a half. So this is 2 over 3 to the half. I need to make this a whole, don't I? Yep. If this was a third, how do you make it to the next whole? 2/3. And that's the idea. So in essence, you've done a little bit of this idea before, but you were just working it with just square roots. We're going to break it into that today too. It seems weird, but it's first hour, they flew right through it, so it shouldn't be a big deal. So let's look at our properties. We know all of our properties. Oh, put them up here. You have these somewhere. It might not be a bad idea to have them again. Actually, I didn't want to put light on. I'm going to put one of them on, just so we have them off to the side also. When you have the same base, different exponents, and you're multiplying, you're just adding your exponents. When you have a base to an exponent, remember we called that power to power. That's when we multiply. We have the a distributive property of an exponent. We have negative exponents. When exponents were negative, they weren't happy where they were, so we moved them around. And it worked the same way. I know the property's not written in on the smartboard about if you have a negative in the denominator. I have 1 over a to the negative m. That's just a to the m. We just made sure that the exponents were always positive, because we like positivity. We don't like this negativity. And then the last ones are when you're dividing. Remember how we talked about it? We played the game of war. We didn't write it kind of how they do on the smartboard here. When you are dividing exponents, if you have the same base, I always said just play war. What that meant was if the exponent in the numerator was larger than the exponent in the denominator, you'd subtract going up. And it was larger than the denominator, you subtract going down. It was just a quick little way of doing it, as opposed to always rewriting to a negative exponent and then reflipping it and going from there. That just wound up being way too much work. So, as you go through a couple of these, I'm just going to kind of walk through a few examples. What's up again? If I have 3 to the half times 3 to the 3 halves, isn't that the same base? Last time I checked, 3 and 3 would have to be the same number. Convenient how that works. So, if I have 3 to the 1 half and 3 to the 3 halves, same base, different exponents, I'm multiplying. What do I do the exponents? Add them together. What's 1 half and 3 halves? 4 halves, otherwise known as 3 to the 4 halves, which is 3 squared, otherwise known as 9. Did we do that when we had variables? So why would I do that when I have numbers? If I had x cubed times x to the 4th, I had same base, different exponents. All I'm doing is that I have now x to the 7th. If I have 3 cubed and 3 to the 4th, what that really means is I have 3, 3, 3, 3, 3, 3, 3, which is 3 to there. I'm not doing that. I'm keeping that base value to go through. That makes sense? Same thing goes for the next one. I have power to power. If I have 4 to the 3 halves squared, that's the base raised to an exponent raised to another exponent. Power to power. Sorry, not as awesome. That wasn't as awesome as rad, but it's right there. So after they made rad, not to jump subjects here because I never do that. All the skateboarders felt left out because skating was starting to get pretty huge around then too. So then Gleaming the Cube came out. Gleaming the Cube was one of Christian Slater's first movies. You know who that is? Well, Dirks, I know you would know because you know things. If anybody in the room catches some of my cultural bad references, you at least you have half a whim of them. So I appreciate that. So I have 4 to the 3 halves squared, power to power. What's 3 halves times 2? 6 halves, otherwise known as 3. And 4 cubed, well, 4 times 4 times 4 is 64. Notice I'm not pressing any buttons on anything. Excuse me. Next one's pretty self-explanatory. There's 2 ways of going about one like this because it's rather clean. I have the quantity 9 times 4 to the half power. Well, according to the property, that means I just distribute the exponent to the 9 and to the 4. So I have 9 to the half times 4 to the half. Or, if you think about order of expo or order of operations, it tells me, please, parentheses, inside my parentheses, I have 9 times 4, which is, and what's the half power stand for? What's the square root of 36? 6. You can do it a couple of different ways. It works. So this is basically the square root of 9 times the square root of 4, which is 3 times 2, which is still 6. It still works. Okay? It still works. And what's nice about doing it this way is sometimes maybe you'll have a 9 and a 7 to the half power. So your answer would be like 3 root 7, things like that. You can do stuff and simplify portions of parts depending upon numbers. Negative exponents, again, when something's raised to a negative exponent, it's not happy where it is. Right now, most of you have a negative exponent above your brain. Well, up where you are. Sorry. So 25 to the negative 1/2 means it is 1 over 25 and a half, which means your answer is 1/5. So if you struggled a little bit with the exponent rules back in chapter, this is going to be good practice to work yourselves through again. I think it was like, I don't know. 6 to the 5 halves over 6 to the half. They have the same base, don't they? You're all right. So if I have 6 to the 5 halves and 6 to the 1 half, I have to start asking myself, who wins in the battle royale? The 5 halves or the 1 half? 5 halves. So then I have to sit there and think and play war. What's 5 halves minus 1 half? 4 halves, which is 2 again. And other people are complaining, well, that's really weird way to write 36. Yes. Yes, it is. No. The 6's don't become 1, because if they become 1, what happens? What's 1 raised to any power? 1. So if you start thinking that if they simplify out to becoming 1, then your exponents have nothing to do with the problem. So this kind of goes with what Brad was saying here. You have to remember, if you treat it again like it was a variable, I think that might kind of counteract any of the silliness there. And then lastly, 8/27 to the 3rd. When you have a 1/3 power, what did that stand for? 2/3. 2/3. Yeah, 1/3. Yeah. Good morning. It stood for a cube root. So what's the cube root of 8? And the cube root of 27? So your answer is 2/3. When we, oh wait, it's the next one. Get ahead of myself. Sorry. My brain is weird. Meh. Okay. Take a minute, simplify those 3, please. Take a minute and simplify those 3, please. I get this a lot on this first one. What's the exponent in the numerator of the 7 that you don't see? 7 to the first power. Because if it was 7 to the 0 power, what would the numerator be? It would be 1. So that means it's 7 to the first power. So in order to play war with the same bases, I don't write it as 7 to the first power. I'm going to write it as 7 to the 3/3 power. Okay? Because what's 3 over 3? it's still 1, isn't it? By doing it that way, you're getting your common denominator right away. So now who wins, 3/3 or 1/3? 3/3. So you get 7 and 2/3 for your result on that. Yes, sir. By writing it as, the only other thing you can do here is the cube root of 7 squared. But Jen, this is kind of what you were getting at. How do you leave it in what format? Usually, you're gonna, if you start with a fractional exponent, you leave it as a fractional exponent. If you start as an nth root, you leave it as an nth root. These two answers are equivalent. One of them is easier to write than the other. Fractions. Because if you go that next step and you accidentally flip those two, then it'd be wrong. You don't get, see what I'm getting at? But if you write it and you know this is 3/3, that's 1/3, you play war, you're good to go. I just did a fraction. Does that make sense? Easier that way. So I have the numerator, I'm sorry, this one, kind of out of the way. All that stuff isn't happy, is it? Since all that stuff is unhappy, I'm going to move all of that stuff to a denominator. I get 1 over 2 to the 4th, 3 to the 4th, all to the 4th. Then what do I do with that 4th on the outside? Distribute in. 4 to the 4th is how much? Yep. So it's 4 to the 4th is 1, because you do power to power, so 4 times the 4th is 1. So your denominator becomes 1 over 2 times 3, 1/6. From where? From here? Okay. This guy's negative. Since it's negative, you're going with the idea that you've got the property of junk to a power. That power just happened to be negative, so I took all the junk and put it in the denominator. From there, I distributed the exponent because it was power to power. So some of these problems you can get multiple parts too. This next one's a little bit weird. The next one kind of gets you into some properties that you may or may not remember from working with just straight radicals. For example, if this was the square root of 12, I don't want to say 12. Yeah, I'll say 12. When you have square roots, do you guys agree that numbers are composite or prime? So numbers can be written as the product of primes or product of composites. You can put them all together. What you can do here is you can say that this was the square root of 4 times the square root of 3. Do you think any of that changes if this is an nth root? No, it all works the same. Those properties still hold true. So in an example like this, when I see that, that means I have the cube root of 12 divided by the cube root of 4. Which means you can break this apart, is that you have 4 to the 3rd times 3 to the 3rd over 4 to the 3rd squared. See what I'm getting out of that? By recognizing that I have a base of the 12 and the 4, since they have the same exponent, that means that they have the same nth root. When they have the same nth root, you can simplify it like you would any other normal square root. So 4 to the 3rd divided by 4 to the 3rd is how much? 1. So you can do your old and you're left with 3 to the 3rd squared. So in this case, I have 3 to the 3rd squared. It's power to power, which means I multiply. 1/3 times 2 is? You're going to use a calculator for that. Shimki, will you take care of him for me? Well, 1/3 times 2. That's your answer. Again, you started with a fraction. It goes, oh yeah, that's how you do it. It is put it together. Please, I apologize that the textbook does a lot of slashy fraction here. Try not to use a slashy fraction. It just makes it cleaner. Which gets us into the same idea. Yes, sir. I don't have any tissue. Give me a second because I got to write passes and I'm in the middle of all this. Yeah, you need to bring some. Sorry. Need one on it? Same idea. The properties of radicals of pulling stuff apart and rewriting them as other like composites and primes and things, all of that still works. And that last example is one of the reasons why it does. As you go through these things, you're going to see this from time to time. It is not going to be anything that's going to be overly crazy. It's going to be the idea that you can. It's not going to be to the point where you're not going to be able to figure out how to set this stuff up. The properties of radicals allows you to be able to do a whole bunch of simplifying, if you guys remember. One of the things that we did is when we simplified radicals, we always look for perfect squares. You guys have no offense, I'm mad at you. We're going to do the same basic idea when we get into cube roots, fourth roots, and all that. Remember the little shortcut trick that I showed you before on how to simplify with your calculator? Remember how to use a table? Vaguely remember that? If I want to do the square root of 12, if I want to simplify the square root of 12, that's an easy one. We know that it's 2 root 3. Okay? If I want to take the square root of 12, well, the square root of 12 breaks out to be the square root of 4, the square root of 3, which gave you 2 root 3. If you go to your calculator and you put in the y equals portion, remember the y equals, I go 12 divided by x squared. If I do that, and I go to my table, the table is going to generate values of x squared and see which one of those goes into it. For example, if you go in here and you hit your table, as I'm looking at, okay, I started, I can't divide by 0, so that's why that's an error. But 1 squared, 12 divided by 1 squared is 12. 12 divided by 2 squared is 3. 12 divided by 3 squared is 1 1/3, and so on and so on. What you were always looking for in your tables there was the last values of numbers before everything goes all decimal. I have a 2 and a 3. That means my result was 2 root 3. Does that ring a bell now? That doesn't change if I'm talking about cubes. It doesn't change if I'm talking about fourths, fifths, whatever. The only thing that's going to change is the exponent of the value of x in the denominator. So if I wanted to simplify the square root of, I want it not square root, excuse me. I want to do the cube root of 108. I know that the cube root of 108 isn't clean, but I know that if I'm trying to simplify that and put it into what we call simplified radical form, what I can do is go to the calculator and I can type in 108 divided by x cubed. And the table will do all those calculations for me to see if there is, in fact, a perfect cube that works. And it's doing the same thing. 108 divided by 1 cube, 108 divided by 2 cube, 108 divided by 3 cube, and so on and so on and so on. You're looking for that last value before everything goes decimals. In this case, where is it at? 3 and 4. So that means that a simplified value of the cube root of 108 meant that, well, that was 27 in the cube root of 4. Because 3 cubed is 27. So your answer would have been 3 cube root 4. That's 3 cubed. Because I'm doing, if you think about it, if you're taking 108 divided by some value of x cubed, I did 108 divided by 1 cubed, so it's 108 divided by 1. 108 divided by 2 cubed, so it's 108 divided by 8. So, yes, sir. Oh yeah, it could possibly happen because you could have, let's say it's a square root of 41. It's not simplifiable, is it? It's the same basic idea. Those same rules will occur where there might not be a perfect cube that goes into it. You start thinking about if you just start thinking about numbers in general, if you start cubing numbers, once you start cubing numbers out, they get real large real quick. All right? We were 8, 27, 64, 125, 216, something like that. So they get real large real quick. So if you're looking for the cube root of 80, and you know right away that 64 is not going to work, 27 is not going to work, but 8 does. So you're going to be able to figure stuff out rather quickly. Okay? The numbers don't get so crazy, whereas in square roots you can have the square root of 164. You might have a 4 that works. You might have something. There's so many more that are out there because the numbers aren't as large. Does that make sense? I think that's where you're getting at. And this works if it's a 4th root, 5th root, whatever. All you have to do is change the denominator to x to the 4th, x to the 5th, and then all that still goes through. It's a nice shortcut because that way you don't have to worry about the other calculus, because that one doesn't do it either. But this one does. So that's like the benefits and things for all these. Which then gets you to be able to do we just did 12. But you want to do the cube root of 54. If I use the calculator, the same principle here, if I want to simplify the cube root of 54, when you type that in, you'll see that 54 winds up being, well, (27). So it's 3 cubed is 27. 54 divided by 27 is 2. So as the calculator will help you with that, your answer would have been 3 cube root 2. So you simplify these the same way as you would earlier, but the subtle difference is that you have an nth root now as opposed to just plain square roots. Okay? Now the weird part. And this is probably the last one we'll have time to do today. When I want to rationalize my denominator, I say it's weird, but it really isn't. It just looks weird. When I have the 5th root of 3/4, using the properties of the exponents, the properties of division and all that stuff, that means the numerator is the 5th root of 3, denominator is the 5th root of 4. Are we okay with that? Just by breaking it apart. We've done that before. That's not a big deal. So that gives you the 5th root of 3, the 5th root of 4. Now, I will say that whenever you're trying to simplify fractions with or rationalize your fractions like this, it's always easier to work with fraction exponents as opposed to nth roots. This is one time that I will say that the nth roots are so much cleaner. So if I want to write a 5th root, what is that as an exponent? 1/5, yeah. So I get 3 to the 5th, 4 to the 5th. Oops. I need to multiply that by some factor of 1 to get rid of the exponent of a fraction. So as I'm going through this, so you still hers? Whatever. So I need to make this a whole. How many more fifths do I need to make a whole? Quattro, as bueno. Quattro gets you cinco. Sorry. Hola, ¿cómo estás? Again, 4 to the 4/5 divided by 4 to the 4/5 is still 1. It doesn't change. But what's 4 to the 1/5 times 4 to the 4/5? 4. You get 4 to the 5/5, which is just 4. And then your numerators go back to 3 to the 5th, 4 to the 5th. I'm sorry, 4/5. Okay. Depending upon if the instructions say leave as fractional exponents or leave as nth roots, if you're doing just nth root, or excuse me, fractions, this is fine. You're done. If you had to go back and rewrite that as an nth root, you'd have the fifth root of 3 times the 5th root of 4 to the 4th over 4. I'm probably going to say it's okay to leave them as fractional exponents in the numerator, but no fractional exponents in the denominator. It's kind of the same idea as that you wouldn't have any square roots in the denominator, so we're not going to have any nth roots in the denominator. So I think leaving stuff with, what's that? Yeah, and that's what I'm saying is that I think it's going to be okay when we rationalize stuff to leave them as fractional roots instead of going back and rewriting, because that just looks messy. All right, we'll get into the parts of the variables and stuff and the adding and subtracting. I don't think we have time to do that for tonight, but actually we do. I did assign a couple of those. What do you think 7 times 6 to the 1/5 plus 2 times 6 to the 1/5 is going to be? 9 times 6 to the 1/5. When you have the cube root of 6 minus the cube root of 2, what do you think you should do to the cube root of, cube root of 16? What do you think you should do to that first? Simplify it and then get common. You're basically combining like terms here. I have a feeling you're going to be okay with that. I don't think you. No, this would be, this is the cube root of 8 times the cube root of 2. So this is 2 cube root 2 minus 1 cube root 2, which is cube root 2. Yeah. You're simplifying the radical before you combine terms. It's just like when you had the square root of 12 minus the square root of 3, you'd get 2 root 3 minus root 3, which is just root 3. It's the same process, but you've got a cube root instead of a square root. Okay. I'm trying to remember what problems I put up there. I don't know if I posted it or not. I did this is in 7-2. It's on page 411. It was 2254, I believe, evens. I think I said evens, or did I say odds? I gotta double check. Oh yeah, it was evens. Was it evens? Yeah. Okay. I don't know if I wrote it down on the online yet or not. So it was. No, it wasn't evens. It was odds. I just remember if I said evens or odds. Odds. It was 23. It was 23.55 odds. It was because that's what I assigned. I have nothing on here. I didn't have anything online. It's much more work to go that route. Oh, I gotta go back here. Let me put this on here. What's that? Right, today's Tuesday, so we're doing page 411. What I say, 23 to 55 odds. Right, this is 7.2. Oh, okay, that's why we're going. That's why I was trying to figure out what the hell you were talking about. That makes a lot more sense now.